So here we have a car accelerates uniformly from a speed of 20 meters per second to a speed of 60 meters per second in 10 seconds. And it says the track of the the radius of the circular track, is 400 meters. And it says when the car reaches a speed of 48 meters per second, find the following. Pause, read if you need to. Other than that, I'm just going to crack it. In order to find the number of revolutions completed, you can find the linear distance completed, and then from there you can convert linear distance to a number of revolutions by going through the circumference of a circle. All right, in order to find delta x here, I'm just going to go ahead and multiply both sides by t, and then therefore delta x is just vf plus vi divided by 2 times delta t. So you notice here I highlighted t in yellow because I don't know what it is. I know vf for this particular part is 48 meters per second. Why? Because this is when the car reaches the speed of 48 meters per second. So here it's important that you plug in 48 meters per second, not 60. Okay, so 48 meters per second is our final velocity. Vi is given as as 20 meters per second, and then delta t is what we don't know, so I'm going to go ahead and find it. So I plug every values in. Vf is 48, Vi is 20, and then the 2 is part of the function here just to find average velocity. What I'm missing is time, so I can go ahead and find the time that it takes to get to 48 meters per second. Well, the problem gives you enough information to find the acceleration. It says here from 20 meters per second to 60 meters per second and a time of 10 seconds. So what I can do is I can find the linear acceleration here by using the information given. Vf here is 60, Vi is 20, and that phenomenon occurs in 10 seconds. So therefore, you can do 60 minus 20, which is 40, 40 divided by 10, which is 4. So we can find that the tangential acceleration and the linear acceleration has a magnitude of 4 meters per second squared. Well, what do we do with this information? Well, once we know A, we can find how much time it would take to reach a speed of 48 meters per second starting from 20. So I'm going to apply the same function that I did here where I'm circling around, except instead of finding A now, I know what A is. I just need to find the time that it takes for the car to go from 20 meters per second to 48 meters per second. Okay, so here Vf is 48, Vi is 20, the acceleration I just calculated, which is 4, 48 minus 20, which is 28, 28 divided by 4, which is 7. So the time that it takes for the car to accelerate from 20 meters per second to 48 meters per second is simply a time of 7 seconds. So once I know that, I can plug in for t and then really just calculate the work here. Okay, 48 plus 20, which is 68. 68 divided by 2 times 7 on your calculator, that should give you 238 meters. But once again, this is delta x. Part A asks you to find the number of revolutions. They didn't ask for the linear distance covered. So once we know the linear distance, we can simply do a conversion. Well, we can start with 238 meters and convert it to revs by going through the circumference of a circle that I said earlier. One revolution is simply one circumference, and the circumference of a circle is 2 pi r. Well, we know what r is. R is given. So therefore, I'm just going to carry my work down. The only thing difference here is that I'm going to substitute out r for 400 meters because that's what it is. And then units here, meters cancels out. So the only thing left is just the number of revolutions. So in this particular problem, during the first, 7 seconds here, to go from a speed of 20 to 48 would take about 0.0947 revs. Okay. All right, that is our answer for part A. Here is another strategy to find A. So hopefully pick one that you like. I can just use my angular displacement function. Angular displacement is simply the initial angular speed or velocity here times time plus 1/2 angular acceleration times t squared. But you notice here I highlighted a couple things because I don't know what omega I is and I don't know what alpha is. But that's okay. I can just go ahead and find it really quick. Well, I know there's a relationship between linear speed or linear velocity and angular velocity by multiplying it by the radius of the circle here. All right, so in order to find the omega, I need to divide both sides by r. So it's simply here, omega is equal to v divided by r. Now that I have an expression for omega, I can use it to find omega I and omega f. Okay. All right, so here I'm just going to go ahead and plug it in. What's the initial omega? I can just go with the initial velocity, which is given here as 20, and then the radius is 400. So if I do that, I will get the initial velocity or angular velocity as 0.05 rad per second in the clockwise direction based on the problem here. All right, on that, I'm going to apply it again because I need to find what the omega f is at 60 meters per second here by using the same strategy. So if I plug in 60 meters per second divided by the radius, I will get a value of 0.15 rad per second. Well, this is my omega I, and then this is my omega at 10 seconds, because that's what the problem says. However, I can use this information to find what the angular acceleration is. Well, the angular acceleration was simply omega f minus omega I divided by change in time. Here, the omega f is 0.15 rads per second. The omega I is 0.05 rad per second, and then the quantity of time that it took to complete this task is 10 seconds, as stated in the problem. So therefore, the angular acceleration here is simply 0.01 rad per second squared, and that's just the magnitude. Well, now I know what alpha is. I can go and plug it in. Once again, the initial angular speed here, or angular velocity, that I converted to is 0.05 rads per second. So I'm just going to go ahead and plug that in. So omega I is 0.05, t is 7 seconds. So at this particular junction, it's important that you know that end use time here is 7. It's 7 because it wants us to find it when for the car reaches 48 meters per second, and that only took 7 seconds. So it's important that you do not plug in 10 for this particular part. Okay. All right. Alpha I just found, and then once again the time is just 7 seconds. We're gonna square that, and then from that you can just do calculator work, and it should give you about 0.595 rad. But this isn't rad. It asks for the number of revolutions, but once we know the number of rad, we can simply convert it to rev simply by saying that for every 1 revolutions, it is just 2 pi rad. So once you go around the circle 1 time, which is 1 revolution, in radians, that is just 2 pi rad. Rad cancels out, therefore we can just get the same answer here. So it's 0.0947 rev. So as you can see, it doesn't matter which strategy you employ, just make sure you stick with the values given, and make sure you pay attention to the time interval here for this particular part. Okay, so that's part A, using a couple of different strategies. Hopefully you like one of them. If not, do it yourself. All right. Part B asks you for the car's centripetal acceleration or radial acceleration here. Here we know AC is v squared over r. Well, we know what v is. V is 48 meters per second, and which is given in, once again, it's just when the car reaches the speed of 48, and then the radius is given as 400. So plug and chug time, and that'll give you a magnitude of 5.76 meters per second square, and it says magnitude. So I would just go ahead and highlight that without the direction, and the direction would just be center seeking anyways. Part C asks you to calculate the car's angular speed. Well, we already know the function or the connection here between linear and angular speed. Simply v is equal to r omega, but it asks for angular speed, so I'm just going to divide both sides by r. V here is 48 meters per second, r is 400. So from there, we can simplify it down to 0.12 rads per second. Okay. So that's our answer, and it asks for magnitude, so I don't need to say clockwise or counterclockwise. If it doesn't, please make sure you include the direction. All right. Here, part D asks you to find the magnitude of the tangential acceleration. Well, in the previous strategy, I actually already found it. So using one of the strategies to find part A, I found A to be 4 meters per second square. So there it is. Okay, we need to re-watch it and then hopefully get there. All right, let's move on to part E. Part E asks you to find the magnitude of the total acceleration. So this one's a little tricky. Total acceleration is really just your resultant vector for A10 and AC. Because the object is accelerating tangentially, it has an A10, but it's going in a circle, so it has to have an A centripetal. So therefore, A total is the resultant vector of those two acceleration components. So here, A10, A is just the square root of A10 squared plus AC squared. Really, if you notice, it's just Pythagorean theorem here. We already found A10 to be 4 meters per second. Once again, I highlighted here 4 meters per second. That is your linear acceleration, or A tangential. Don't forget to square that. And then AC here, we already found it in part B, which is 5.76 meters per second square. So really here, I'm just going to plug and chuck the two values I already calculated. So therefore, if you simplify this on your calculator, you should get about 49.18 underneath the radical. And then the square root of that will give you about 7.01 meters per second square. And that is your answer. And this is magnitude. So once again, I am done. All right, stay nerdy. Don't be black.